This is Professor Rogers. In this video, we will look at the analysis of contingency tables in SPSS. You might also know contingency tables by another name, cross-tabulations or crosstabs for short. Contingency tables are a technique that we use when we have two variables and both of them are categorical. There are a variety of analyses that are done in relation to the contingency table. So we can look at the table visually to see how things are related, and this could give us a direction if we have ordinal data. Contingency tables have a goodness of fit statistic, known as chi-square. Chi-square is used to tell us whether the deviations from a random distribution of observations in the cell of the table are statistically significant. We also have several measures of effect size, and which measures we use depends on the type of categorical data that we have. So if both variables are ordinal or binary, we might use a gamma or Kendall's tau b. If at least one of the variables is nominal, we would use phi or Kramer's v. As an example today, we're going to look at state-level data, and we're going to look at a hypothesis that relates education and policy on the death penalty. In particular, we are going to claim that as the educational level of the residents of a state goes up, the likelihood that the state will have the death penalty goes down. So the claim here is that as people get more educated, they become more enlightened and are more likely to think that the death penalty is cruel, and therefore they don't implement it. Down below here, we have the frequency tables for the two variables. So we have 32 states that have the death penalty. Notice with education how it is coded. The value of 1 is assigned to high, 2 to medium, and 3 to low. This is ordinal data, so keep in mind that we can arrange the data in any order we want. So I could go 1 equals low, 2 equals medium, 3 equals high, but how this is arranged is going to be an issue for how the computer looks at this. In order to get to our procedure, under Analyze, we go to Descriptive Statistics, and then we select Crosstabs. This is the command dialog box that we get under Crosstabs. Normally, we put our dependent variable in the rows, and we put our independent variable in the columns, which is what I have here. That's not a hard and fast rule. You might want to switch them around if you have so many categories in your columns that they start to run off the page. But if you were to do that, you would also flip around some of the other statistics that we're going to talk about later on. You can select what information you want in the cells of the table. So here I've selected the observed values, what we actually see as a count in each cell of the table. And also I'm going to select the column percentages. That's pretty common to do, to look at the percent distribution within your independent variable. And that's going to show you the relationship between the two variables fairly quickly. So here is my resulting crosstab in SPSS. I've highlighted here the row for the totals and also the column for the totals. What we do is we call this part of the table the marginals. It has a special name, and we'll see its importance in just a bit. There's also this one cell in the lower right-hand corner, which is the grand total, or I sometimes call it the total total, to emphasize how we are combining the row and the columns. Here's the column itself. So you'll notice in the cells of the table, we have the number of observations in each cell. So among no death penalty states where the value is 0, we have, and that are high in education, we have 7 states. And within the high group of states, that's 78% of the states within the high group do not have the death penalty. You'll notice that the column does total 100%. So that's a good way to double check to make sure that you have your percentages set up correctly. Here is what the table looks like without the column percents, and you can set your data that way. Some people recommend that if you have less than 100 observations, they suggest that you do away with the column percents completely. I'm not of that school of thought myself, but if that's what you want to do with less than 100 observations, that's fine, and this is what your table would look like. You just don't click the column percents in the cell dialog. Now, with this table, we can eyeball the table, and we can right away see what our relationship is. So notice that when we look at with states having the death penalty, within the educated category, that's only 22% of the states. And that percentage goes up as the level of education in the state goes down. So that's in line with what we were saying at the beginning. It's an inverse relationship between education and the death penalty. And this is very clear, this relationship, because we limited our percents to column percents. So we can look at those and it tells us very clearly what's happening. Some people make the mistake and look at the count itself. The raw numbers don't really tell us anything. They need to be standardized, and that's what the column percent does. The chi-square statistic is selected in a different option, which is called statistics. That's on our dialog page, and so it's up right up here in the upper left-hand corner. So when we click on that, we get below the contingency table a second table with chi-square tests, and here we have those results. I normally suggest that you take the Pearson's chi-square simply because that is fairly common across different statistical packages. So our Pearson's chi-square is 9.766 with 2 degrees of freedom, and the statistical significance is 0.008. Now, the likelihood ratio chi-square is also a common one, and some people do prefer that one, but because it's not in every statistical package, I simply prefer to use the Pearson chi-square. Notice the results come out very close. Normally, it will not create a large difference over which one you select over the other. Down at the bottom, there is this little message. This is a warning message. It says 1%, 16.7%, I'm sorry, one cell, 16.7%, have expected count less than 5. And so we will look at that a little bit. We'll identify where that is in the table and why that's such a big deal. But for the moment, we're going to work through the chi-square calculation. This is the formula for chi-square. So you notice that thing with the x squared next to it. Chi is the Greek letter chi. For each cell, we have as our denominator the expected value in the cell. And then in the numerator, we subtract the expected value from the observed, and we square that. So that is kind of like going out into Euclidean space like we did with the standard deviation. Your question is going to be, how in the world do we get the expected value? We know what the observed value is from our previous crosstabs. So this is how we're going to do that. We start with the marginals of the table. Keep in mind, way back at the beginning of the course, one of the things I said is to keep in mind what your benchmarks are. That statistics are just not numbers that fall out of the sky, but they're points of comparison. And in the case of the contingency table, your point of comparison is tied to the marginals of the table. And what we're going to do is we're going to try to create in the cells of the table what the table might look like if the observations were randomly distributed given the value of the marginals. And here is how we do that calculation. So for each cell, we take the row total for that cell, multiply it by the column total for that cell, and then divide by the grand total. This is what that looks like when we calculate that. So here's the equation for each cell within the table calculated based on the marginals. So this is our expected value. So we work that out, and here we have two tables. On the top, we have the observed values, which we saw from our earlier analysis in SPSS. We had SPSS generate this. And then down below is the expected value for each cell of the table, which we just calculated. Obviously, the computer is doing this calculation. I just showed you how it gets that calculation in this example. So here we work it out. So with each cell, we subtract the difference between the observed and the expected in the numerator and square that and divide it by the expected value. And that ends up to be 9.766. That by itself doesn't mean anything. We'll take a look in a moment of how we establish the statistical significance based on that number. Let's look at this error message. So the problem here is that in one cell, it's specifically where in states that do not have the death penalty but have high education levels, the expected count is only 3.2. You'll get this warning message if you get any cell in your table that has an expected value of less than 5. Now, why is that? Let's go back and take a look at the equation. The expected value is in the denominator. Well, as we go towards 0, that is going to inflate the value of the chi-square contribution in each cell. So imagine what would happen if the expected value was 0. We'd have a complete breakdown in the analysis. We can't have that. As you know from math, you just can't do that calculation because that goes up to infinity. But if we have only 1 or 2 expected observations in a cell, that potentially inflates our chi-square statistic. So SPSS is not saying do not do this analysis, but it's giving us a warning that our chi-square might be inflated. So we might, if we could, try to find ways to perhaps consolidate categories or do the analysis slightly differently. In this particular case, we don't have a lot of choice. We were just handed those 3 categories of education. But if we had multiple categories, we could reduce them. For those of you watching this video from my stats classes, we will actually show you using a different technique down the road with a one-way ANOVA. You can do an analysis such as a Bonferroni analysis or another kind of analysis that might be helpful in locating where you might collapse cells, but not today. And now we got to calculate the degrees of freedom. So the meaning of degrees of freedom in a contingency table has to do with, assumes that you know the marginals so that they are as they are given, your benchmark. And then the question becomes, how many more cells do you need to fill in the value for in order to complete the whole table? So you don't need every cell in a table to do that calculation. Now conceptually think about what that means. In data analysis, we often try to emphasize the fact that we're reducing the amount of information that we have. So if I have a table and I have to carry around the value for every cell, that's more cumbersome than if I only have to carry around the value for some of the cells. So this is the calculation, degrees of freedom, that gives us the minimum number of cells which we need to fill in to get from which we could then calculate the rest of the table. So here's the calculation here for our particular table. The degrees of freedom is 2. So what we have is we have a chi-square statistic of 9.667 with 2 degrees of freedom. We take that information and now we can look at the chi-square distribution. Now don't panic, we're going to show you a graph and a table. SPS does the calculation for you and just spits out a statistical significance number. But we wanted you to understand where this comes from. On the left, what we have is a graph of the chi-square distribution. And notice that that distribution changes shape as we increase the degrees of freedom. So that's different from the normal distribution, where every normal distribution has the same shape regardless. Chi-square will change with the degrees of freedom. That produces this table here So we want to exceed a particular critical value. That is, we want to be on the right side of that curve in order for a result to be statistically significant. And you'll notice that within each probability expectation, that the value of chi-square goes up as the degrees of freedom increase. Now, why does it go up? Well, you need a bigger chi-square because you're being less inefficient. You're being less efficient as we increase the degrees of freedom. So that's why we need a bigger chi-square. So we're trying to find something in the right edge of the table. What's that cut point in the right edge of the table? In our example, if we want to get a p-value of 0.05, or we want to get statistical significance of 0.05, we would have to have a chi-square of at least 5.991. So our actual calculation, remember, was 9.667. So that's how we can say that the statistical significance meets our 0.05 threshold. Now there's some other statistics that can give us effect size and sometimes direction. And these are gamma, Kendall's tau B, phi, and Kramer's V. There is on the dialog box for the crosstabs a statistics button, the same one we use to get the chi-square, that allows us to select these additional statistics. And so I have done that here. When we interpret these statistics, we use the same thresholds for effect size that we would use with Pearson's R. So to be a weak relationship, the effect size statistic would have to be at least 0.1, to be moderate at least 0.3, and to be strong at least 0.5. This is a convention, so some people might take like 0.26 and round it to 0.3. I tend to use absolute thresholds. We're going to start with a statistic called gamma, which gives us both effect size and direction. And we use this when both variables are ordinal or binary. Reason why we're going to spend a lot of time with this is to learn the logic. There's another statistic that I prefer more, Kendall's tau B in this situation, but it's easier to teach the logic of this. And what we're really concerned with here are what we call ties. So we're going to have positive ties, which we're going to call P, and we have negative ties, which we're going to call N. That leads us to this formula here that I've highlighted in red. So in the denominator, we add together both sets of ties. So that's like all of our ties. And then above, we look at the difference between positive and negative. So if we have more positive ties than negative ties, we're going to have a positive relationship, or the likelihood is going to increase. If we have more negative ties, there's going to be a minus sign. So here I'm going to summarize the positive ties in this table. So where we go is we start with the low value. So death penalty is 0, and the lowest value for education, keep in mind, is 1. So even though that's high, from the standpoint of the computer, that sees that as a value of 1. So that's our low value. So we're going to start at 7, and we're going to then look for wherever there's motion into a different column. So we're going to go from 7 to 18, which is the yes medium cell. So that's going to be a positive direction. We're going to go from 7 to 12, which is a yes low. That's a positive direction. Then we're going to jump over to medium, and we're going to go 9, 12. That's a positive direction. Now we're going to do the same thing the other way. So we're going to go from 2 to 9, from 2 to 2, and then from 18 to 2. And that's going to give us our negative ties. Here I've highlighted in red the actual calculation. So we have 318 positive ties, 58 negative ties, and we work out the calculation, and that gives us a 0.69 gamma. That is, remember, our threshold for strong is 0.5, so that's going to be a strong relationship. The question is this really positive? Well, it's not. So from the standpoint of the computer, because of the way education was coded, it sees it as positive. But this relationship is actually negative. We are saying that as education increases, the likelihood that a state will have the death penalty decreases. So that's one of the things about contingency tables, because with ordinal data, you can change the order from lowest to highest to lowest. You actually have to look at the table. You just can't report the number. You got to look at the table to understand the direction. Now, here we have a table, and we have gamma and Kendall's tau B laid side by side. These two measures are similar but different. The difference is in the denominator. So in gamma, we had to have that motion to the higher or lower value. In Kendall's tau B, we will also look at the ties within a column, those places where there are no motion. And we do that because some people think that gamma inflates the size of the relationship. And we see that here. So the gamma in our example is 0.691, whereas Kendall's tau B is 0.396. So that drops it down to a medium relationship. We also have on the far right, we have the statistical significance. It's in this column called approximate significance. So I myself, in this situation, would favor the use of Kendall's tau B. I would encourage you to print out both, actually, just to see if something's going on, because sometimes there's not going to be a big difference, but in this case there is. Now, if we have one variable that's nominal, that automatically excludes the likelihood that we can have direction. So we use some different statistics in that case, and these statistics are based on the value of the chi-square. So in a 2x2 table, we use the statistic phi, and here you see the calculation for phi. It's the chi-square divided by the number of observations, and then we take the square root of that. In other tables, we would use Cramer's V, and you'll notice there's a adjustment in the denominator in Cramer's V for the number of categories that you have, your degrees of freedom in your table. So that as the table gets bigger, there would be a larger adjustment to the Cramer's V. Now, both of these values are going to give us a positive value that are going to range from 0 to 1. So we can interpret them the same way as we would Pearson's R, gamma, and Kendall's tau B. When we actually see that value, we're just not going to get direction. So here I have all 4 of my measures of effect size printed out in the same output. And you'll notice in this case that phi and Kendall's Cramer's V come out to be the same value. Also notice how close phi and Cramer's V are to the Kendall's tau B. So that's also helps us understand some of the value of Kendall's tau B. It gives us usually gives us a much more similar relationship to the other measures than we would get with gamma. Okay, so what did we learn today? We use contingency tables when both variables are categorical. We have to visually inspect the table to make sure we understand the meaning of results. The coefficients are not adequate for that. If there is direction, we will see that, but keep in mind, not every categorical variable is one that can be used in an analysis of direction. So if at least one of the variables is nominal, there is no direction. The goodness of fit measure is the chi-square. So we use the chi-square to determine whether or not there are deviations from the random distribution of observations in the cells of the table. And that's what gives us statistical significance of the fit. We can use gamma or Kendall's tau B to give us the effect size and direction when both variables are ordinal or binary. And then if at least one of the variables are nominal, we can't have direction, but we can still have effect size. And that is done through using phi or Cramer's V. Thank you for listening to this video.